Good evening. Welcome to Late Night with Kate. I'm your host, Kate McTighe, and I'm going to be talking to you guys today about a recipe that I've made dozens of times in the lab and that is really essential for any burgeoning lab rat. So this recipe is for PCR, which is short for polymerase chain reaction. And what a polymerase chain reaction does is it takes a target piece of DNA, in the orange here, and it amplifies that piece of DNA over and over and over again until you get thousands, millions, billions of the DNA that you want in a little reaction tube. So PCR was invented by Dr. Kary Mullis in 1983, and his recipe is world famous and used a lot and is award-winning. It's been awarded with the Robert Koch Award, the Japan Award of 1993, and most notably the Nobel Prize in Chemistry in 1993. The recipe for PCR is kind of analogous to that of baking a cake, for example. So first off, our ingredients are going to be target DNA. So hopefully you've isolated some DNA that you want to amplify, and it's pure. So the target DNA serves as kind of a base or something of substance that we put the rest of our ingredients into. So it's kind of like the milk or the water of making a cake. So we're going to put in, I've got some water here, we're going to put in, that is our target DNA. And then you're going to add primers to it. These are DNA primers. They are short segments of DNA, usually 12 to 20 base pairs long, that attach to the 3' ends of each of the strands of your target DNA and then will allow your polymerase to bind on and synthesize new DNA. So primers are kind of the catalyst. They make things happen, they're going to allow things to rise, so it's like baking soda in a cake. So we're going to put in some baking soda here. And then after you've added that, you need nucleotides. You need your A's, T's, C's, and G's all separate from one another. These are your individual nucleotides that will add on and serve as the new material for your new DNA that you're amplifying. So this is the bulk of the material that you're using in PCR. It's the bulk of the material that you're using in your recipe for making a cake. So it's your flour, your sugar, your vanilla, your spices. So we'll add some stuff in here. Flour, sugar, some vanilla. You want to add in your nucleotides in relatively equal concentrations because DNA is comprised of relatively equal concentrations of A's, T's, C's, and G's. So we've got that. And then, probably most importantly, you have your DNA polymerase, and so this serves to make new strands of DNA. So it's going to bind on to your primers and then use the nucleotides to make more DNA. So polymerase in the early days of PCR was isolated from animals, and it was slow and inefficient, and you had to keep adding more polymerase in halfway through your reaction. It was no good. So then scientists figured out that they could isolate a polymerase from a bacteria called Thermus aquaticus, which grows at high temperatures. So the polymerase works at high temperatures. So it's much faster, more efficient. You can leave your PCR and go do other things. So it's much nicer. So we call that polymerase TAC for Thermus aquaticus. And your TAC polymerase is going to be something that binds things together. So it's like an egg in the recipe. So we've got some eggs here. Okay. And then finally, we're going to add some buffer and ions to our reaction mixture. And so normally we use divalent ions for PCR. So we use manganese and magnesium ions. And so this is like adding our final pinch of salt to our cake mixture. So we're going to do that. And then we're going to mix it up. So when you're running your PCR, you want to make sure that everything is really sterile and free of DNA and RNA, because if any genetic information gets into your reaction tube, then the polymerase is going to amplify that as well, and you're going to get contamination, and it's going to ruin your PCR and all of your hard work, and your colleagues are going to laugh at you. So make sure that this is very, very sterile. So now that our ingredients have been thoroughly mixed, now we need to program our thermal cycler. So normally PCRs run 20 to 40 cycles and take 2 to 4 hours to complete. And so in each cycle, there are 3 distinct temperature phases that we have to go through. And the first of those 3 stages is the denaturation step. So we need to take our double-stranded DNA and we need to convert it into single-stranded DNA. So we need to break the hydrogen bonds between the base pairs, and we do that by heating the sample up to 95 degrees Celsius. And that goes on for 20 to 30 seconds per cycle. So that's the first temperature stage. The second stage is the annealing phase, and that is where our primers are going to attach onto the pieces of single-stranded DNA. So the temperature for this is more variable because it depends on the melting point of the individual primers that we use. So a general rule of thumb is that for every A or T in your primer, you will have 2 degrees, and then for every C or G in your primer, you will add 3 degrees. Because C's and G's have 3 hydrogen bonds between them, and A's and T's only have 2 hydrogen bonds between them. So a good point of reference is we do this around 65 degrees Celsius, but if you want to be more precise, then you should do the math yourself. So the third and final stage per cycle is the elongation phase, and that is where Taq polymerase binds onto the primers and then starts synthesizing the new piece of DNA. So Taq has an optimal temperature of 72 degrees Celsius, so the temperature we set for that is 72 degrees Celsius, and that goes for a variable time depending on the length of your target DNA sequence, because Taq, as a general rule of thumb, will synthesize 1,000 base pairs per minute. So depending on the size of what you need to be synthesized, you should adjust your time accordingly. So once all of those temperatures and times and the number of cycles are set on your thermal cycler, then you're good to go to load all of your samples and stick them into the thermal cycler. And turn it on, and then wait until it's done, 2 to 3 hours. So we're back. It's been a couple hours, so let's check on our PCR, final product. Ooh. The perfect PCR. This will be the envy of all of my colleagues and my lab mates, and I'm sure yours will be too, and I'm sure that you will get an A on your research credits this semester. This has been another episode of Late Night with Kate. Thanks for watching. Good night.